error analysis. So one table in that one column of the table has error, and but error is quite easy for derivative calculation. There's not much difficulty. It is for the first derivative. Okay. So again, we go back to the formula for error in the Lagrange interpolation. Now this formula, you see, this coming probably for fourth or fifth time. So this is a Lagrange interpolation formula. So fx is a real function, and I approximate it by p and x. So difference is e and x. Okay, that's error with endpoints. Okay, so the error with endpoints, and we derived this. Well, I didn't derive it. I stated it. Fn zeta divided by n factorial product x minus xi. Okay. Now I want to compute the derivative, so I just take the derivative of this. Okay, and compute at a given xj. Okay. Now we can take the derivative of this. Okay, and it happens to be this function product xj minus xi, but I not equal to j. If I equal to j, then it becomes 0. So I not equal to j. And the derivation is pretty straightforward. You take a log of this, log of product. I will not do this stuff. And log of this product becomes sum, right? Sum of x minus xi. And follow this after that. Okay. And then substitute x equal to xj. You will get that. Now, so what is the error? In fact, this is the error in the derivative, right? So this is e and x derivative at xj. Right? This error in the derivative. This should be actual derivative, but I don't get actual derivative. I am computing this. So that's error. So this error in the derivative. And I mean, only ambiguity is the zeta. Okay, so zeta I really don't know. I mean, zeta is somewhere between this and between 2 points, the leftmost point and the rightmost point. But other than that, I have this product and n factorial. So we need to estimate. This guy will estimate what is the maximum value and what is the minimum value. In any case, this one for uniform h, you can know the number, right? For uniform h, what is this number? So there are how many terms? N minus 1 terms with n points, right? With the 3 points, there will be 2 terms. X0 minus, depends on where. For x0, I will do, it will be x0 minus x1, x0 minus x2. It's in fact 2h squared. But if we ignore this factor, p-factor, which is some number, 2, 3, 5, and so on, it is h to the power n minus 1 by dimensions, okay, divided by n factorial. Okay, and of course the prefactor I don't know, but in mathematics or in computation, we always are interested in order of the error. If h is tiny, then you don't worry about prefactor, factor 2, factor 3, that doesn't matter. Our error is in fact h to the power n minus 1. Okay, h in fact is pretty tiny. You should be choosing 10 power minus 2 in non-dimensional units, 10 power minus 2, 10 power minus 3, and we do that. Okay, so error is order h for n minus 1. Okay. And that is what is listed in the table. Maybe at the end I will show you the table stuff. So, but we can also derive several interesting conclusions from this formula. So if f is a polynomial of n minus 1th order, so if this is that polynomial, okay, or I written that. So the derivative is accurate, no, with n points, because what happens to this guy? If it is n minus 1th order, this becomes 0. Okay, so with 2 points, linear function will have exact derivatives. With 3 points, quadratic functions will have exact derivatives. With 4 points, cubic function will have exact derivatives. And it follows because these polynomials are exact representation of the function. Okay, and that I told you before. So that thing continues, and is all because of this derivative, this one. So this formula is very useful, even though I didn't derive it. It's very useful formula. Okay, so yeah, so let's do an example. Now I have the table here. I mean, you probably can see is error is listed in the right hand side with the 2 points. It's pretty tiny in my tablet, so it is order h, right? Because hn minus 1. With 3 points is order h squared. Okay, double derivative will be one order less with 3 points, right? One more derivative. So in fact, you can do it for dimensional argument. It's product of x minus xi for first derivative, and if you do the second derivative, it will be one less. Okay, so that will be the thing. So in any way, so with first derivative, the derivatives are order h minus 1, and you'll find it everywhere. With 3 points, it is order h squared. With 5 points, is order h4. Okay, it's pretty small, but h4. Okay, now with double derivative is one order less. Okay, so with 5 points, with 3 point double derivative is order h. I think there's another typo here. This should have been h cube double derivative. Okay, so I will just check that this one is a typo, and the numbers I need to double check. Okay, now let's do a real calculation, and with real means for ideal function x squared. So I take 3 points. So this function I know the exact derivatives, but I take 0, half, and 1 x. And what is y or f of x? 0, 1 quarter, and 1. So 3 points. Okay. Now let's compute central derivatives. 3 points I should get exact or non-exact. Will I get exact derivatives? Yes, we will get exact. With 3 points, it is polynomial x squared polynomial. It will be exact. Okay. Now let's see. So I'll do central first, which is easy. Central derivative will be y at the endpoints. So y at x equal to 1 minus y at 0 divided by 2h. So it is 1 minus 0 by 2h. What is h? H is half, huh? Right? H is the difference between the nearest neighbors. So 2, h is half, so it is 1. Right? Okay, why am I getting? So first derivative is at the mid. First derivative at the central point is 2x. Okay, 2x. Okay, exactly. So this is my answer, numerical answer. Num answer. And what is the exact number? So f prime x at half is, take the derivative 2x at x equal to half. What is that? 2 by times half is 1. So they match. Correct? Now let's look at forward derivative. So I'll do the forward derivative, or let's do a double derivative. What do you do double derivative? So y1 minus 2y half plus y0 divided by h squared. So y1 is 1, 2 minus y half is 1 quarter plus 0 by h squared, 1 quarter. Okay, so this gives you half by 1 quarter, which is 2. And double derivative is indeed 2. Okay, so this is my y double derivative. Okay, so that's what we get. And now I can also do other derivatives. No, I mean forward derivative. Let's do forward derivative. I have less space left, but I do forward derivative with 3 points. So I should use this table here: minus 3, 4, 1, 4 minus 3, 4 minus 1. So minus 3 y0 plus 4 y half plus minus y0. Okay, divide by 2h. So divide by 2h is 1. Okay, so this is my y prime at 0. So minus, so y0 is 0. So the first one is gone. Second one is 4 by 1 quarter is 1 half, right? 1 half. Right? 4 times 1 half minus y0, which is 1. So this is 1 quarter. Y half is 1 quarter. Value of 1 quarter, right? Excellent. Thank you. So this is 1 minus 1 is 0. And indeed, the first derivative at x equal to 0 is 0, 2x, and it is 0. So we can get all this with 3 points exactly. Okay? Just to tell you, if I had only 2 points, then what happens? If I just use 2 points, 0 and 1, then my values of the function is x, and value of the function is 0 and 1. Then if I compute the derivative, there will be error. Huh? And you can see the error. So y prime at 0 will be 1 minus 0 divided by h is 1, right? For this case. Error with 2 points, the forward difference will be 1. And the derivative, in fact, is 0. So we get an error. Okay. So we need 3 points for this function. With 2 points, of course, you can compute, but there will be errors. And please note that I used for 3 points, h is half. It's not a tiny number. I mean like what Newton said, or the Newton Leibniz said, h should be small. So h is not 10 power minus 6 or 10 power minus 10. It is half. Still, we get a pretty accurate numbers. Now, one more remark. If you are doing astrophysics, you know that the points are too far. When if you are using this length as light years, right? So I may choose 100 points or 1,000 points or even 10,000 points for discretizing. And if the lengths are light year by 1,000, we still pretty large, right, in terms of kilometers. And if you take the derivatives, there will be a lot of errors with large numbers. So you non-dimensionalize it. So your h is small. Okay. So non-dimensionalization has another advantage as a result. Okay. Okay. So that's what I wanted to say today. And so this is about derivatives.